Have you ever looked at the sheer complexity of the universe and wondered, is there a hidden code keeping it all together? Well, today, we're going to look right past the surface-level chaos of the physical world to find the elegant, underlying mathematical rules of symmetry. We're talking about abstract algebra, specifically an introduction to mathematical groups. Now, don't let the word algebra intimidate you. By the end of this explainer, you're going to see exactly how everyday logic perfectly mirrors the deepest rules of mathematics.
Okay, let's dive into this by thinking about something super familiar, the Rubik's Cube. It's got billions of possible configurations, literally billions. So how do mathematicians even study the moves you can make without getting entirely lost in that chaos? The secret is, they don't look at the cube itself. Instead, they look at the rules of the moves. Think of it like this. Whenever you make a move on the cube, you can always make another move. You can combine moves, you can choose to do absolutely nothing, or you can perfectly reverse any move you just made. This exact set of operational rules is what mathematicians call a group. And groups are, quite literally, the language of symmetry in our universe.
So here is our roadmap for today. We'll start with a symmetry puzzle using the Rubik's Cube. Then we'll unpack the 4 rules of a group. After that, we'll dive into calculation applications using Cayley tables. And finally, we'll wrap up with abstract proofs using some really simple analogies.
All right, Section 1, the 4 rules of a group. Demystifying the axioms. We're going to break down these axioms, and honestly, you'll quickly see that the underlying math is something you already intuitively understand just from navigating your daily life. But first, let's establish our official definition. A group is simply a set which we'll call G, equipped with a binary operation represented by a little star symbol. We write this out as G, star in parentheses. Now, don't let the abstract letters throw you off. G is just a collection of things, and the star? It's just a placeholder for a physical action, like adding, multiplying, or twisting that Rubik's Cube. Oh, and a quick side note, if the order of your operation doesn't matter, meaning A star B gives the exact same result as B star A, we call that an abelian group, which basically just means it's commutative.
So what are the 4 rules that are set in operation absolutely must follow to be considered a group? Let's pair every single mathematical term here with a physical analogy so it sticks. Rule number 1 is closure. Think of this as the safe zone. It just means if you take any 2 elements in your set and combine them, the result is still trapped inside that set. You never break out of the sandbox. Rule 2 is associativity. This simply means when you're grouping 3 or more actions, the order in which you group them doesn't matter. The total outcome is exactly the same. Rule 3 is the identity element. I love this one. It's the do-nothing element. It's an action that leaves your starting object completely unchanged, kind of like adding 0 to a number. And finally, Rule 4 is the inverse element. This is reality's undo button. For every action you take, there's a specific corresponding action that perfectly reverses it, bringing you right back to the identity or the do-nothing state. Moving on to Section 2, calculation applications, Cayley tables. Time to put these rules to the test with actual numbers.
Now, what's really interesting about this is how a Cayley table visually organizes things, almost exactly like a multiplication grid. We can test mathematical sets like addition modulo 4 or multiplication modulo 8 by solving for their safe zones, identities, and undo buttons to prove they act as true, mathematically valid groups.
Let's walk step by step through the Z4 modulo 4 example. The operation here is addition modulo 4, meaning we add numbers, and if the total is 4 or more, we divide by 4 and just keep the remainder. Step 2 asks for our identity. Well, if we add 0 to any number, it stays the same, right? So our identity, E, is 0. But step 3 is where the magic happens, finding the inverses. What brings us back to 0? For the number 1, we add 3 to get 4, which has a remainder of 0. So 3 is the inverse of 1. But look at the number 2. 2 plus 2 is 4, which gives a remainder of 0. This means the number 2 is its very own inverse. No way, right? To undo the action of 2, you literally just do 2 again.
Let's try another one. The U8 group. This time our set is just the numbers 1, 3, 5, and 7, and our operation is multiplication modulo 8. Step 2 shows our identity here is 1, because multiplying by 1 changes absolutely nothing. Now, let's find the inverse of 5. If we multiply 5 by 5, we get 25. Divide 25 by 8, you get 24, with a remainder of 1. Since 1 is our identity, multiplying 5 by 5 brings us right back to the start.
So the crucial point is that in this specific group, 5 is its own inverse. Actually, scratch that. It's not just 5. If you test all the numbers in the U8 set, 3 times 3 is 9, remainder 1. 7 times 7 is 49, remainder 1. Every single element in this group serves as its very own undo button.
Which brings us to our final section, abstract proofs, simple analogies. We're going to prove these rules using everyday logic.
I know, for a lot of beginners, abstract proofs sound super intimidating, but I want to reassure you right now, if you understand the basic logic of driving a car or just putting on your shoes in the morning, you can easily master mathematical proofs. Think about this intuitive question. Can a car have 2 steering wheels? Imagine a car where 2 people are trying to steer in completely different directions at the exact same time. The whole system would fail. A car, by its very nature, can only be controlled by 1 steering wheel to maintain order. Well, in mathematics, this exact same logic applies to the uniqueness of the identity theorem.
The theorem states that a group can only ever have one identity element. To prove this, mathematicians use a fun little trick. We just assume the impossible. Let's pretend a group has 2 identities, which we'll call E and E prime. If E is the identity, then multiplying it by E prime must just leave E prime unchanged. So E times E prime equals E prime. But wait, if E prime is also the identity, then multiplying E by E prime must leave E unchanged. So E times E prime equals E. Do you see what just happened? Both equations equal the exact same combination. Therefore, mathematically, E absolutely must equal E prime. The 2 identities are mathematically forced to collapse into the exact same element. The identity is strictly unique, only 1 steering wheel allowed.
Now consider this everyday quote. When you get dressed, you put on your socks, then your shoes. When you undress, you must take off your shoes first, then your socks. It's incredibly obvious, right? I mean, you can't take your socks off while your shoes are still on. Well, this daily routine perfectly illustrates our next abstract theorem, the socks and shoes property. It basically states that if you want to find the inverse of a combined action, you absolutely must apply the inverses in reverse order. And this brilliantly illustrates exactly how the algebra confirms our daily routine. We want to prove that the inverse of A combined with B is B inverse combined with A inverse. We test this by multiplying them together. In step 3, we shift the brackets using our associativity rule. This puts B right next to B inverse, in the middle. Well, an element hitting its undo button becomes E, the identity. Now we just have A times E times A inverse. The E does nothing, so it just vanishes. Now A is right next to A inverse. They annihilate each other, leaving just E. The shoes come off, then the socks come off, leaving you at the identity. It is a perfect mathematical collapse.
We've seen how abstract symbols perfectly map to the physical world, from Rubik's Cubes to just getting dressed in the morning. These axioms aren't just abstract ideas on a chalkboard. They govern the safe zones and undo buttons of reality itself. Which leaves us with a really fascinating question. If mathematical groups dictate the rigid rules of symmetry, are they actually the hidden source code of our physical universe? Keep questioning the rules of the world around you,